Hello friends, I am Dr. Narendra Jakhar from Department of Physics, University of Rajasthan, Jaipur. First of all, I welcome you all to this 2-week refresher course in physics, and I am really thankful to the Ramanujan College and its Teacher Learning Center for providing me an opportunity to interact with the young folks entering in the physics teaching. So today we are going to discuss about X-ray photoelectron spectroscopy, XPS, and overview. So this is a very beautiful and fine characterization technique, especially for the material scientists. So in this lecture, we will try to look into different aspects of the XPS, its advantages, what informations can be obtained from the data, how can we record the data, what are the different types of the different components of the XPS. This talk is especially designed for the newcomers in the XPS. So I will try my level best to keep this level as much as possible to match with you directly. And since I know that this is in the online mode and you will watch the recorded videos, so in between the talks, in between the slides, I will put some questions from myself and try to answer those questions in between. And so this talk will resembles or look like one-to-one interaction. So let us start with the talk. So we are starting it from, I'm taking this. So we are starting from the discussion of XPS and overview. So these are the contents of my presentation. First, we will talk about the introduction, that what XPS is and how can this XPS be used to analyze the surface of any sample, and how can we take the different data of the information we can obtain from the sample, and followed by the history and background. From my point of view, it's always necessary to have a peep into the history to getting a better idea of the scientific developments. So, since we are going to introduce this XPS, a very fine and very beautiful characterization technique, so it is very essential that we should know that what are the different scientific contributions among the globe to reach XPS up to this level, and then followed by the basics and working principle of XPS. In this particular content, we will try to take different examples of the basics from the ranging from the photoelectric process to the OJ electron emission and different equations used in the XPS, and some few more examples to get very in-depth idea of its working, followed by the instrumentation of XPS. Particularly in this content or in this topic, we will try to look inside the different uh, steps or the different instrumentations include in the XPS. What different parts of the XPS are, and what is their uses, and what should be their values to get the optimized data, and so on. And then further we will discuss about data analysis, that how can we get the data, record the data, and which are the different softwares used for the data analysis, followed by the conclusion. So briefly, this is what the contents of this topic and this presentation. So introduction. So XPS, also known as ESCA, ISCA, that is electron spectroscopy for chemical analysis. This is a very beautiful and fine technique for analyzing a material's surface chemistry. So here the focus is on surface chemistry of the material. XPS can measure elemental composition as well as the chemical and electronic states of the atoms within a material. So it is a surface chemistry. It provides the idea of the surface chemistry. So the data obtained from the surface is up to only 1 to 10 nanometer of the depth of the material. Means up to only the 3 to 4 different atomic layers from the sample surface. So it is a very surface sensitive technique. When we irradiate the solid surface with the beam of X-ray, and the electrons are emitted out or knocked out from that surface, and if we able to measure the kinetic energy of the electrons, that is what coming out from this particular range of 10 nanometer up to depth from the material surface. So a photoelectron spectrum is recorded by counting ejected electrons over a range of kinetic energies, and these energies and intensities of the photoelectron peaks enable us or the provide us the idea about the identification and quantification of all surface elements except hydrogen and helium. So this is what some historical background of this XPS. Since XPS uses X-rays, XPS uses electrons, XPS is based on the photoelectric effect, XPS is known or relying upon the atomic models provided by the different scientists. So this slide provides us a in-depth idea that who was who and what were the different contributions among the different scientists. So in 1895, Roentgen discovered X-rays, and this is what a milestone discovery for material science and for the health physics. And this is what a very beautiful historic photograph. This is the hand of Mrs. Roentgen, and she was wearing his marriage ring in her ring finger. So this photograph is very popular and related the historical aspects with the origin or with the finding of XPS. And then later in 1897, Sir J.J. Thomson discovered electron. This discovery is also a very important milestone for the development of physics. And today's all new technology is governed by this electron discovery of Thomson. And photoelectric effect. This is what a very fundamental aspect and a very fundamental effect on which this whole X-ray photoelectron spectroscopy relies. So Hertz was the first scientist who reported the photoelectric effect in 1887. This is what the Hertz experiment. Hertz was actually studying uh, electromagnetic waves in space, and he used two metal balls and apply a voltage difference between them, and there is what a spark produced between them. Hertz observed or noticed that whenever the ultraviolet radiations falls on one metal block, one metal ball, then this spark is prominent. Spark is more supportive, more favorable by the this ultraviolet uh, incident of radiation on the one of metal uh, ball. But Hertz did not carry on this observation further, and he was limited himself to study the electromagnetic waves. Later on, Leonard studied the experimental findings of the photoelectric effect, and but interestingly, in before 1900 or before 1905, there were no classical there were no classical principles to support this Leonard's findings of photoelectric effect. So later in 1905, the great scientist Einstein explained this photoelectric effect on the basis of photon is energy quanta, and this discovery or this explanation of Einstein leads the quantum physics or leads the physics into very new direction, and it opens new horizons for the physics development. And later, during the time 1911 and 1913, Bohr and Rutherford proposed different atomic models, and Bohr proposed that the electrons are revolving around different orbits. They are known as stationary orbits, and their orbital energy is increasing as we go outside the energy levels, the n equal to 1, n equal to 2, and n equal to 3. So this is a brief idea about the history. In later 1920s, H. Robinson, a former colleague of Rutherford's and an XPS pioneer, wrote that an accurate knowledge of the energies associated with the different electronic orbits within the atoms is essential to the further development of the theory of atomic structure. So in 1920s, Robinson claimed that by having the idea of energies associated with the different electronic orbit will provide us the more tools to peep into the atomic structures. So still this is what we are using it. So Robinson was the XPS pioneer. Later on, after 3 decades, yes, it take a lot of time to get the idea of XPS, to get idea of XPS feasible or into the real world. It was the Sibens group in 1954 who was the first to invent or made this first high resolution system for XPS, which they preferred to call electron spectroscopy for the chemical analysis, or SCA, and used it to record the spectrum of cleaved sodium chloride. Here is some interesting story of Sibin. Sibin awarded Nobel Prize for this discovery of X-ray photoelectron emission, XPS or SCA, in 1981. Sibin was a Swedish physicist, and his father, the Sibin Senior, was also a Nobel laureate. He got the Nobel Prize in 1924 on the X-ray physics. So these both father and son duo worked in the same field, and interestingly, Sibin got his PhD degree under the supervision of his father only. So this Sibin family, the Nobel Prize is what Sibin family is a business, Nobel business. So basics and working principle. So this is what we already talked, that this is very surface sensitive tool. The sensitivity of XPS is limited to the depths less than 10 nanometers beneath an object surface. See, this is what, don't take it as a disadvantage of the XPS, that it is what limited to the 10 nanometer of the depth of the sample surface. This is what advantage. How this becomes the advantage? Since sometimes many of the scientists are interested in the surface chemistry only, and if we are talking in the terms of nanotechnology, if we are talking in the terms of thin films, then there we would like to get the idea of the one by one films layered on one to another. So this XPS will provide us the exact idea of the thin film chemistry or the surface chemistry. So in this picture, this is what X-ray beam. X-ray beam can penetrate up to 1 micrometer of the depth inside the sample volume. So this is, the X-ray can travel. There is no problem for the X-rays to travel a larger distances or larger depths in the samples. And this whole volume, suppose that this is 1 into 1 centimeter square area, or the volume exposed for the X-rays, and this electrons can be excited in the entire volume, and but the electrons coming out from the surface is only from a very thin layer, that is what, less than 10 nanometer beneath the sample surface. And this is a zoomed view. Here you can see this red part is up to 10 nanometers or 3 to 4 atomic layers, and so the electrons are coming out from a very small solid angle, and this area is what, 1 millimeter square. So a very small area and a very small depth is what is observed from this XPS, and these electrons are extracted only from a narrow solid angle. So this slide tells us about the different basics and working principle of the XPS. Since we know that in XPS we send X-rays on the sample surface, these X-rays knocked out electrons, and we will study the kinetic energy or the binding energy of the detected electrons. This binding energy and kinetic energies are related with each other. If we know the kinetic energy, we are able to find out the binding energy of the electrons coming out from the particular atom in element in sample. So the kinetic energy of an electron measured by an XPS system can determine the energy with which that electron was originally bound by its host atomic nucleus. Here I would like to take a pause and digress the topic again. There are enormous number of electrons in the sample surface, and there are different types of the elements present on the sample surface. So nature provide us the different elements, different electrons sitting in the different atomic orbits. But the beauty of the nature is these all electrons have the characteristic binding energy associated with a particular nucleus or the particular atom. And this beautiful observation provides us and enables us to identify the electrons coming out from which orbits and provide us the idea about electrons coming out from which element. So the idea of the binding energy in turn depends on several factors. The atomic element present on the sample surface, the orbital previously occupied by the electron, and the orbital's chemical environment. So so again, suppose that our carbon is present in the sample surface and carbon is making I'm taking a pen here. Okay, and suppose that carbon is making what different bonds with the C C or C with O and C with double bond O. Suppose carbon is making different bonds. So this XPS tells us that these different C's, how much of the portion of the C makes a C single bond C, how much of this C makes and a single bond with O, and how much of this proportion of C makes a double bond with O. Since this C1s electron has the different binding energies when it is associated with the different chemical environment like carbon, oxygen with single bond, oxygen with double bond. So that this enables us to find out the different idea of this chemical environment. And it is in this way that XPS can be used to measure the elemental composition, that since we know that C1s binding energy is different from the O1s binding energy. So the electrons coming out from the carbon having the different peak and the electrons coming out from the O1s having the different peaks. So it also provides us the elemental composition, empirical formulas on the basis of the elemental compositions and their proportion, and the chemical state and the electronic states as we discussed in this here. So this is very valuable information when we are going to study the sample surface. In this slide, we will see the X-ray generation. This is what the famous Cooley's tube, in which we apply a high voltage between the cathode and the anode. So anode can be any material. It may be aluminium, ale, it may be magnesium, and so on, any metal surface. And this cathode emits electrons when it is heated up. So this is known as thermionic emission. When this cathode is heated, it emits radiations, and these radiations are attracted to this positive potential, and they travel towards this anode surface. So when these accelerated electrons falls on the anode surface, they actually come to the rest, and when they come to the rest, they emit electromagnetic radiations. This is what a very fundamental principle of the electrodynamics, or the classical electrodynamics, that accelerated charge particles emit electromagnetic radiations, and X-ray is part of electromagnetic radiations. So when these electrons falls on this anode surface, they provide us X-ray, and this continuous falling of these accelerated or the energetic electrons on this anode surface heated this anode, and the more heating create some problems of the melting and another problems. So to avoid these problems or to overcome these problems, we need cooling of the anode material continuously. So this cooling is done through a chiller. So whenever you are going to see the X-ray photoelectron spectroscopy system in any university or in any research center, you will always see that there is a chiller associated with it. So this tells us the requirement of the chiller, why it is essential. And these emitted X-rays are having such kind of the spectrum. Here we can see that this is what a continuous shape of the spectrum, and here is what a horn type X-rays. They are known as characteristic X-rays. So this continuous X-rays are coming through this classical explanation of the electrons acceleration, and since the electrons are coming to the rest by colliding with this anode material, so they are what this process is known as Bremsstrahlung process. And the origin of this characteristic X-rays is what the characteristics of this anode material. So this K alpha and K beta are the characteristic X-ray peaks of this anode material. Suppose that this is aluminium, then this is aluminium K alpha and aluminium K beta. And what is the physics behind this characteristic X-rays is discussed in this slide. Okay, so when electron incident on the uh, anode material, then this may knock out a 1s electron. Suppose that this electron is knocked out, so this is what a secondary electron. So here is what a vacancy in the lower state, 1s state. This vacancy can be filled by the upper level electrons. Suppose that this vacancy is filled by this 2p electron here. So the amount of energy of the difference between the energy levels of 2p and 1s is getting ejected in the form of photons, and these X-ray photons are collected by us, and this is what the X-ray generation. Sometimes it is also interested to know that this excited energy is not directly converted to the X-ray photons. This excited energy is directly going to give this rise to this emission of this 2p electron, and this is 2p electrons are known as OZ electrons. So we will discuss in the forthcoming slides. And when this incident X-rays falls on the sample surface, so this time this is what the atom present in our sample. So these are the energy levels of the atoms. In the previous slide, this is what the figure was for the anode material. So now X-rays incident on the sample surface, and this atom, the 1s electron is knocked out from this atom, and these incident X-rays, which electron is get ejected depends on the several factors, and this is what a probabilistic events. So this electron 2s electron can also be ejected here. The 2p electron can also be ejected from this interaction with the incident X-ray. Suppose that this is 1s electron. So this is a law in the interaction of the radiations with the matter, that the more bound the electron is, it has more probability to getting photoelectric effect. So this is what a photoelectric process in which the incident X-ray knocked out a electron from the sample surface. So 1s electrons are more probable to show photoelectric effect rather than 2s and 2p. So they are also probable, but more probability of getting 1s is more. So this ejected photoelectrons will give us a peak on the XPS spectrum, and this correspond to the 1s peak. Suppose that electrons are ejected from this 2s level, then these ejected electrons, photoelectrons, will give us a different peak that correspond to the 2s peak. And suppose that electrons are getting ejected from this 2p peak, then the binding energy of these 2p electrons are different than this 1s and 2s electrons. So they will rise us to a different peak in the XPS spectra, and that's on. So XPS spectral lines are identified by the shell from which the electrons was ejected, rather 1s, 2s, 2p, and so on. The ejected photoelectrons has this kinetic energy. So this is what the famous photoelectric equation. The kinetic energy equal to h nu minus of binding energy of the electron minus of phi. This is what work function. Following this process, the atom will release energy by the emission of photon or an Auger electron. Since we are going to record only electrons or the ejected electrons, so again this is a vacancy here, and the vacancy can be filled by the uppermost electrons. And if this uppermost electron fills this vacancy, then either a photon will emit of the X-rays, or sometimes this whole energy is delivered to this 2p electron, and this 2p electron get knocked out by this excitation energy. So uh, the emission of the X-ray photon and the coming out electrons, which is known as Auger electron, is a competitive process. So this slide will give us the idea about Auger electron emission. This Auger electron emission, since this is electron, again will give rise to a different peak, and these peaks are known as Auger peaks. Since this vacancy is filled by this 2p electron, and this 2p electron level is L2, L3, and suppose that LL. So this peak is identified. So this peak is identified as KLL. So this is coming from LL level of an electron to the K shell electron. So this energy will give rise to a different peaks, and these peaks are known as Auger electron peaks and the XPS spectrum. Okay, in this slide, how the different informations can be obtained by having the uh, different orbits of the electron. So how can we able to identify the elements and compounds? Suppose that this is nucleus and this is electron here. The more the attraction of the nucleus on the electron will lead us the more binding energy. So suppose that the more attraction of the electron on the electron of this nucleus will give rise to the more binding energy. So we know that 1s electrons of any atom has more binding energies than rather than 2p electrons, because they are more outer electrons than 1s and then 2s electrons. So binding energies of the 1s is the highest, then this 2s electron, then this 2p electrons. So if the electrons are coming out from the 1s, they give rise to the different peaks, 2s to the different peaks, and 2p to the different peaks. This is what the case for the pure elements. When we are discussing about the pure elements, then this will the case that 1s, 2s, and 2p different peaks will rise into the XPS spectrum, and we will look after later on in the spectrum that these are the peaks. So you are able to recognize that, and you are able to resemble that. Okay, and since we give us the idea that we can also able to find out the different chemical environment of the elements present in the surface of the specimen. So here we are taking the carbon oxygen bond. Since carbon and oxygen have the different electronegativity, so the electrons are the bond of the electrons of the bond is more oriented or more shifted towards the oxygen. Here we are taking this example. So these electrons are what more shifted towards oxygen. One second. So these electrons are more shifted towards this. So this time C have a positive charge. So to detaching a electron from this C is more difficult than the C bond. And further, suppose that we are having the C double bond O. So this will give rise to the different peaks as we discussed earlier also. So this electronegativity effect will give rise. So here is what at different peaks of the carbon. Suppose that this is the peak from the carbon. So here binding energy is increasing in this way, and this is intensity I. So this first peak is for the CC. The second peak here is for the CO, and this third peak for the C double bond O. So we, by having the idea of electrons binding energy, we are able to find out the different chemical environment and the electronic environment this carbon is going to face in the sample surface. So this is XPS energy scale. XPS is spectrum is usually pressed on the energy binding energy scale. So on the x-axis we are usually going to take binding energy, and this is what the famous equation for the photoelectric effect. So binding energy is equal to the h nu minus of kinetic energy of electron minus of phi spectrometer. So this is for conducting samples. When our samples are conducting, then you can use this information, this equation. So here is the binding energy of electron, kinetic energy of electron, and the phi spectrometer work function. So this equation is valid only for the metal samples, or more precisely we can say that sufficiently conductive samples. And the samples and the spectrometer are in this case when the sample is conducting, then it has a ohmic contact with the system or spectrometer, which causes their Fermi level to align. So we are going to see this into the next slide here. So here is what the energy level diagram of the sample. Here is the energy level diagram of the spectrometer, and this is what the Fermi level of the sample here. And since the sample is what conducting sample, so spectrometer and uh, uh, sample Fermi levels are on the same level, on the same uh, vertical level. So this is what due to the conducting samples. And this h nu is the photon energy of the X-ray. So what is this equation becomes here? This can become h nu equal to binding energy plus phi sample plus kinetic energy of 1s electron. So this is what the equal of this vertical height. So this binding energy is what h nu times of phi s minus of kinetic energy of 1s electron. And since this is what phi s is what work function of the sample surface, but this is what for the conductive samples the Fermi levels are on equal. So when these electrons are ejected and again come to the spectrometer, this is what the energy read by the spectrometer. So this equation becomes binding energy equal to h nu minus of phi spectrometer minus of kinetic energy prime of the 1s. So here in this equation, phi spectrometer comes out or evolves rather than the phi work function of the sample. This is sample spectrometer energy level diagram for the non-conducting samples. For the non-conducting samples, when the electrons ejected from the sample surface and go to the spectrometer, they will give rise to the Fermi level. That is what the difference of the potential between these two Fermi levels is shown as ECH. This is also known as charging effect. So when a non-conducting sample is used by us, so the Fermi levels of the sample and spectrometer are getting some difference, and this will give us the wrong binding energies of our peaks. So to make it right or to make it correct, we are using a flood gun here. Flood gun is what continuously bombarding electrons on the sample surface for make it level up equal to the spectrometer level Fermi level. So a relative buildup of electrons at the spectrometer raises the Fermi level of the spectrometer relative to the sample, and a potential ECH will develop here. This is charging effect. So in the later on slides, we will talk about the instrumentation of the XPS, and we will discuss about the flood gun, the requirement of the flood gun. So, till now uh, we have discussed the different basic and working principles of the XPS.